Hi guys, we're back to talk more about the hydrosphere, water, and this time we're going to talk about the water cycle and in particular evaporation. So let's get started. Okay, so I think most of us have heard of evaporation before. You probably know that when you turn on the stove and you heat up the water and it starts to boil, that's the water evaporating, turning from a liquid into a gaseous form of H2O or water. We've also seen water like evaporate out of a puddle on a sidewalk, or evaporate off our skin after we sweat. So it's probably not a totally new concept. The process of evaporation is part of a more complex picture that kind of illustrates how water moves around our planet. And we call this the water cycle or the hydrologic cycle, hydro meaning water. So just kind of a fancier word for the water cycle. And a model is basically something that simplifies a process that happens in the real world. In as it simplifies it, it acts as a tool that allows us to better kind of comprehend and understand what's going on. So the water cycle is kind of a series of steps that water moves through as it moves around our environment. And in reality, the true movement of all water in all ways at all times is a very complex process. This particular image shows certain kinds of transport of water, water moving as precipitation, water moving as precipitation in the form of snow, water percolating down into the soil, infiltrating from the surface into the soil in the first place, moving through streams, moving through groundwater flow, evaporating out of the water and off the ground into the atmosphere. And so, of course, that shows a certain number of processes. And that in and of itself is kind of an oversimplified illustration of where water is truly moving. And then, the simpler the model is, the less accurate it is, but it can still serve as an important tool that helps us understand. So you also maybe heard of a more simplified version of the water cycle that just includes evaporation, the movement of liquid water into the atmosphere, condensation, the movement in the atmosphere of gaseous water back into liquid water, and then precipitation, the movement of that water back down to the ground. And so we're going to kind of focus on those three steps of the water cycle and try to understand those as a kind of oversimplified but kind of fundamental way that water can move around between different pools or reservoirs on the Earth's surface. So we're going to start out with evaporation. Here's another picture of the water cycle, also oversimplified. But within this, you can see that evaporation moves out of the oceans, out of bodies of water and lakes and rivers, where water can move from that pool or reservoir into the atmosphere. But then, of course, it can also come out of living organisms. So it can come through plants, through the process of transpiration, which is basically like plant sweating, perspiration from animals, and then also from like soils. It can move from that way. And all those processes share the same basic fundamentals, which is it's just the movement of a liquid form of water into a gaseous form of water and transporting it from the surface of the earth into the atmosphere. So, as we already said, evaporation is the process of converting this liquid to a gas. In this picture, I have over a pond where evaporation is certainly taking place. You can see all these little droplets of water above the pond, this kind of steam or this kind of fog. And a lot of people think that is maybe evaporated water. But in fact, that's actually condensed water. You can't see evaporated water, it's invisible. So whenever you're seeing this kind of steaminess or fogginess above the ground, it's actually liquid droplets that you're seeing. Evaporation is actually an invisible process. But another thing that I want to mention about evaporation is that it is a process that requires energy. And so if water is going to be evaporated, it needs to pull energy from its environment to allow that evaporation to happen. And in that process, it actually cools down its environment. And this is a little bit counterintuitive to some students who are first learning about evaporation because they think that we need to heat things up, hot things are evaporating. And that's true. We're putting energy into a system to get the water to evaporate, but the water itself is actually stealing energy from the environment to allow that to happen. And in some cases, actually leaves the environment around it cooler than when it left. Actually, in all cases, it does that. So that's why we have an adaptation to sweat. We put water on our skin, and then when the water evaporates, it steals some of the heat from our body and helps cool us down. This is why dogs stick their tongue out to kind of pant and get evaporation off their tongue to help cool them down. And that's because evaporation is a process that requires energy and therefore steals energy, cooling its environment down around us. So this water then goes into the air, and once it's in the air, we refer to it as humidity. So when we talk about humidity, we're talking about the amount of water that's in the air as a gas, okay? And in general, a really important concept that helps us understand weather is to know that the hotter air is, the higher the temperature it is, the higher the water holding capacity is. So the more energy that air has in terms of having a higher temperature, the better that air is going to be able to hold these water vapor, which is another word to say gaseous form of water molecules. So for example, up at the North Pole or the South Pole, there's about 0.2% water in the air by volume. The air is very, very dry there because the air is so cold that it can't really hold very many water molecules. On the other hand, near the equator, the air is almost 5% water by volume because it's so hot that it has the capacity or has the energy to be able to hold lots and lots of water vapor. So it's a much, much more humid environment. So there's a couple different ways that we can report humidity. You can report how much water is in the air by weight. You can report how much water is in the air by volume. But the most important, or I don't know if it's the most important, the most kind of commonly used way to communicate and report about relative humidity or humidity is in a form that's called relative humidity. And so what relative humidity tells us is what percentage of the potential water holding capacity that a certain air mass could take on is being currently filled up by air. So is it totally full based on the temperature of the air? Is it 100% relative humidity? Is it at capacity? It can't hold any more moisture? Or is it only 50% full? Is it 50% relative humidity? Is it 80% full? Could it hold a little bit more, but it's mostly full? That would be 80% relative humidity. And so the relative humidity is a good measure because it allows us to kind of understand how the air behavior will change based on how full the air is based on the actual conditions of the air. Whereas knowing just how much weight of water in the air might have a really different impact on the air's behavior if the air is really hot or really cold. So the relative humidity depends on a combination between how hot the air is, because we know as the air heats up, its water holding capacity expands. And it also depends on how much moisture is in the air, because if there's more moisture, then the air is more likely to be filled up than if there's less moisture. But both of these variables can move back and forth and can change the relative humidity picture. So for example, you could from day to night have the exact same amount of moisture in the air, but as the air heats up in the afternoon and cools down at night, the relative humidity could change, even though the amount of total moisture in the air has remained constant. So it's sometimes a little conceptually difficult for students to understand, but it's a good way to think about relative humidity because it really helps us understand how the air is going to behave. Okay, so the rules of evaporation, how much water we're going to get into the air, which is going to determine how humid the air is going to be, are going to depend on four main variables that can shift throughout our environment. So the first variable is the temperature of the water. And I think most of us would understand that the hotter the water is, the more likely the water is to evaporate, and the faster that evaporation process is going to happen. So if you want to evaporate water off the stove, you should turn the stove on and heat the water up, and then you'll get it to boil faster and faster. Okay, and even if the water on a stove or out on a sunny day isn't at the boiling temperature on average, there's always going to be some molecules within the water that are moving fast enough, that are hot enough to be able to evaporate at any given moment, even if most of them are not. So that's why we can get evaporation even if we take the temperature of the water and it's not like at the boiling point at 212 degrees Fahrenheit or 100 degrees Celsius, which is the temperature that on average we would expect water to evaporate at. Okay, so thinking of temperature, it's not only the temperature of the water that makes a difference in terms of how fast evaporation happens, but also the temperature of the air that the water's moving into. As we've already said, the warmer the air, the greater the water holding capacity. And so the air has a better capacity to kind of grab onto and continue to bounce around and hold that water in it. And so the hotter the air is, the better it's going to be able to do that. So the equator is going to be better adept at evaporating water than the polar regions. Then another factor that we need to consider is humidity, as we've just mentioned. So in the case of humidity, the higher the humidity, the actual lower the rate of evaporation is. So the opposite is true. Instead of being more humid, increasing the rate of evaporation, the drier the air is, the more evaporation will happen and the more quickly that evaporation will happen. So this is kind of similar in concept to the term right before, the temperature of the air, because we know that when the water is dry, then the relative humidity is very low and there's a lot of available water holding capacity. So it's easier for the air to take on more moisture. So when the air is hotter or when the air is drier, both of those things are going to open up water holding capacity in the air and allow for an easier and faster transition of water into the air. Okay, and then the final factor is windiness. And so windiness is actually just something that decreases humidity. And we just learned before that the drier the air is, the faster it can evaporate moisture. And so what windiness does is it just continually removes humid air and replaces it with dry air in contact with places that are evaporating moisture. So you can imagine, like, if you wash your hands and then you put them in front of one of those hand dryers that they have at many public bathrooms, what's happening is the wind is blowing across your hand, and then at any given moment, some of the water in your hand is evaporating into the air. But instead of allowing that humid air to pool up right above your hand, which will then slow down the continued rate of evaporation of water off your hand, aka drying of your hand, the dryer blows that humid air off your hand and replaces it with dry air. So then more water will evaporate into that until it's filled up, and then the wind will push it and keep replacing it with dry air. This is the same way like a hair dryer works. And this is why in like windy conditions, your lips get really chapped because of this loss of moisture. So here's my little comic. We have a snowman holding up another snowman, and he has a hair dryer, right? A hair dryer is increasing the temperature of the air. It's increasing the temperature of the ice, which in this case is going to lead to melting, not evaporation, but similar concept. It's also going to increase windiness. It's going to decrease humidity. All these things are going to contribute ultimately to the demise of this water-based snowman. Okay, so if we think about where evaporation is happening on the planet, we would expect it to happen where where the water is warm. So we think about all these warm currents in the ocean, like these western boundary currents that we talked about, the Gulf Stream, the Kuroshio current in Japan, etc. We can see that's where a lot of water evaporation would be happening. Less evaporation would be happening to create less humid conditions, and the places where these eastern boundary currents are bringing cold water down, like along the coast of California, along the coast of Western South America, along the coast of South Africa, etc. We can also think about where the air is warmer, which we know is along the equator. We can think about where the air is drier, where it's less humid, which actually we've learned is around these high pressure zones, around 30 degrees Fahrenheit, or sorry, 30 degrees latitude. And then we can think of places where it's windy, and we've learned about some of the wind so far. So to save time, we're not going to go through all of these maps, but you can imagine that all these conditions are changing in different environments around the real world. And so these are the controls over how much water is going to be moving from the surface up into the atmosphere through the process of evaporation. Okay, that's a good stopping point.